Welcome to the lesson of the day. Today we are going to derive the bending equation. Now, for us to derive the bending equation, we are going to consider a section of a beam, or in other words, longitudinal section of a beam, just a part of it. Now, figure 1 shows longitudinal section of a beam with two layers. We have the neutral layer, or in other words what we call the neutral axis, and we have another layer RS whose distance from the neutral axis is y. That is the distance from the neutral axis to the layer RS. Now, we are considering a small section of the longitudinal section of the beam, and we know very well that when a beam is loaded either with point rods or uniformly distributed rods, or a combination of all those rods, the beam usually adjusts itself so that it is able to accommodate the loads that are subjected unto it, and it does that by bending simply. Now, after the beam has been loaded, it will bend in this form here, whereby the layer RS is going to change to R prime S prime. The layer PQ that is on the neutral axis is going to change to P prime Q prime. The distance between the two layers is y. Now, let the layer P prime Q prime subtend an angle of alpha at the center of the arc. The reason being, when the beam bends, it will bend in form of a curve, and we can consider that curve to be an arc of a circle. Remember, an arc of a circle is just part of a circle. So the center of this arc of the circle is O. Now, before the beam bends, these two layers have got equal lengths, and therefore initially, before the bending of the beam, layer PQ is equal to layer RS. Now, arc P prime Q prime, or layer P prime Q prime, is subtending an angle of alpha at the center of the arc of the circle, and the arc, this arc here, have got a radius of r. Therefore, the length of layer P prime Q prime is going to be the radius of this arc of the circle multiplied by the angle subtended at the center of the arc, which is alpha. Likewise, R prime S prime, R prime S prime is going to be given by, that is its length, is going to be given by, now the radius of this arc is going to be the radius of this arc P prime Q prime minus the distance from this layer P prime Q prime and R prime S prime, which is y, and therefore R prime S prime will be given by R minus y multiplied by the angle subtended at the center, which is alpha. Now, the strain in rear RS is going to be given by change in length all over the original length. The reason being, the upper section of the beam will be subjected to compressive stress, and stress usually results to strain. Strain is the deformation that is caused by stress, and that deformation usually results to change in the dimensions of the body that is subjected to stress. Therefore, the upper section of the beam is subjected to compressive stress, and the lower section of the beam is subjected to tensile stress, whereas the neutral axis is not subjected to any stress. That is the reason as to why it is known as neutral axis, because it is not subjected to any stress, and therefore at the neutral axis there is no strain. The neutral axis is not deformed in any way. Therefore, the layer RS will be deformed because it is subjected to compressive stress, and therefore the strain in RS will be given by changing length divided by the original length. Now, this is going to be strain in RS, that is the symbol of strain, that's known as sigma, is equal to, the changing length will be given by original length, which is RS, minus the final length, which is R prime S prime, all over the original length, which is RS. Now, we have said that initially, before the beam bend, the layer PQ along the neutral axis, that is PQ, was equal to RS. Likewise, the layer PQ before the beam bend will also be equal to the layer P prime Q prime after the beam has bent. The reason being, PQ is at the neutral axis, and we have seen that at the neutral axis the beam is not subjected to any stress, and therefore if the beam is not subjected to any stress at the neutral axis, then it means that there is no strain, and when there is no strain there is no deformation, therefore there is no change in length, there is no change in dimensions, and therefore PQ will be equal to P prime Q prime. Up here we have PQ is equals RS. Down here we have PQ is equals P prime Q prime. Therefore you can also say that PQ is equals P prime Q prime is equals RS. Now, when we substitute RS with P prime Q prime at this point here, we are going to have the strain in RS will be given by RS, which is also equal to P prime Q prime minus R prime S prime all over RS, which is equal to P prime Q prime. Now, this will result to P prime Q prime is R times alpha, therefore R times alpha minus R prime S prime is equal to radius minus y into bracket multiplied by alpha all over P prime Q prime, which is R times alpha. Now, when we carry out this calculation here, we are going to have R times alpha minus R times alpha, that is going to be 0, plus y times alpha. Now, y times alpha divided by r times alpha is going to be y all over r, because alphas will cancel each other. Therefore, strain in Rs will be given by y divided by radius. Now, from the topic of simple stress and strain, we know that strain is given by stress all over the Young's modulus of elasticity. Therefore, we can substitute this E here with the stress divided by the Young's modulus of elasticity. And therefore, we are going to have stress all over Young's modulus of elasticity being equal to y all over radius. We can equate in that form. Now, this equation here can be rearranged. Therefore, rearranging the equation, we can rearrange it in this form: stress all over y, stress all over y is equal to Young's modulus of elasticity divided by radius.